Hey, here's another gas problem. Let's see. This one involves 1 mole of a diatomic ideal gas, initially at 1.2 times 10 to the fifth pascals. It's heated at a constant volume from 300 kelvins to 500 kelvins, and then it's cooled back to 500 kelvins at constant pressure. And we're going to ask ourselves, what is the final pressure? And we're going to calculate delta U, Q, and W during each of the stages of this process. Okay, so actually, first of all, since this is a two-step process, first thing I'm going to do is I'm going to go ahead and sketch this out on a PV diagram. That's something that never really hurts to do. Okay, so our first process is one in which the gas is heated up at a constant volume. If the volume is constant, that means that the process is going to be represented on this by a vertical line. And since it's heated up at a constant volume, that means it's going to go up. So something like that. And then it's cooled back to 300 kelvins at constant pressure. And a constant pressure process, since pressure is the vertical axis, constant pressure means it's going to be a horizontal line, and we're cooling it so it goes that way. Okay, so our gas starts out here and it ends up here. Okay, at here and here it's 300 kelvins, and at this point here it's 500 kelvins. Okay, so anyway, first thing we want to know is the final pressure. So let's see, this is one of those kind of ideal gas before and after problems. And so we can work this out by saying, well, P1 V1 over T1 equals P2 V2 over T2. Okay, where 1 is this point down here and 2 is this point up here. Okay, and let's see, this process, the volume is constant. All right, so really this V2 and V1, those are going to be the same, so they just cancel out. So really I've got P1 over T1 equals P2 over T2. Okay, so this is 1.2 times 10 to the fifth pascals divided by 300 kelvins equals P2 divided by 500 kelvins. And this tells us then that P2 is equal to 2.0 times 10 to the fifth pascals. That's the pressure here. But of course, since our second process is isobaric, that is, it takes place at a constant pressure, that's also going to be the pressure here at the very end of the process. And so that's my final pressure there. All right. Now we're going to calculate delta U, Q, and W during the first stage of the process. Okay. Let's see. Let's start out by looking at what kind of process it is. It's a process which takes place at a constant volume, which means right away that W equals 0, right? The work we're talking about here is the work done on the gas as it changes volume, as it expands or gets compressed, but it's not doing those things, so there is no work. Okay? Let's see. As for delta U, well, delta U equals N C sub V delta T. Okay. Let's see if we can figure it out that way. N is the number of moles. We've got that. C sub V. Okay, we're told it's a diatomic ideal gas, so we can get a value for C sub V, and the change in temperature is 200 kelvin, so we're going to be okay there. So C sub V for a diatomic ideal gas is usually going to be 5/2 R, so we're going to say delta U is equal to 1 mole, let's see, 5/2 times 8.314 joules per mole Kelvin times 200 kelvins. And so delta U is equal to, oh, let's see, where is that? 4,160 joules. Okay? And then Q, at this point, there's actually a couple different ways we can get Q. Okay? One is to recognize that because this is a process at constant volume, okay, that means we can write Q is equal to N C sub V delta T. Okay? And since we just calculated NC sub V delta T, that's actually, okay, notice it's also equal to delta U here. So we just calculated that already. This is 4,160 joules as well. Okay? Which makes sense because remember delta U equals Q plus W. And since W is 0, that means delta U is just Q. All right, so let's get to the second stage of the process. Okay. Let's see. This is a process with constant pressure. Okay. Constant pressure means that I can calculate W by minus P delta V. Okay. Although I don't have any information about volume, I can probably go ahead and get volume. I could get volume using the ideal gas law, but let's see if I can get away without doing that. Delta U is equal to N C sub V delta T, which is 1 mole times 5 halves times 8.314 joules per mole Kelvin, okay, times the change in temperature. It's going from 500 back down to 300, so my change in temperature is minus 200 kelvins, and so this leaves me with minus 4,160 joules. Okay, so that's delta U. Okay, that makes sense because basically the internal energy just depends on the temperature. All right, and so if we raise it to from 300 to 500 and then lower it from 500 to 300, we're just going to be back to where we started on internal energy. Let's see, Q, because the process takes place at a constant pressure, I can write Q equals N C sub P delta T. Now C sub P is equal to C sub V plus R, which is 5 halves R plus R. This R is basically, you can think of this as 5 halves plus 2 halves, which gives me 7 halves R. Okay? And so I can say Q is equal to 1 mole times times 7 halves times 8.314 joules per mole Kelvin times minus 200 kelvins, which gives me minus 5,280 joules. So that's Q. Okay, so I've got delta U, although you probably can't read it. I've got Q. And finally, I say delta U equals Q minus W, or plus W, sorry. Let's see, this is minus 4,160 joules equals minus 5,280 joules plus W, and that's going to give me W equals 1,660 joules. So 1,660 joules of work are done on our gas here. And so we've calculated everything we said we were going to. So I guess we're done.